All right, let's get cracking. We only have, as you can see, a few more hours of lectures, a lot really in this course. We're currently here. We'll cover units, the end of unit 6 and unit 7 next week, and Anna will come and give a nice perspective seminar, which I highly recommend watching. And Yoni's going to finish up with some fun machine learning and like statistical kind of inference kind of things at the end. So yeah, that's where we're at. So if we remember, yesterday we covered quite a lot. It was all about this event simulator. So we didn't write one event simulator, we didn't write 2 event simulators, we wrote 3 event simulators, and getting more and more complicated. So the first one, remember, was very much a custom code that just solved this one problem. And the second one was a little bit more customizable in that you could put in a few functions to configure like the timings, like how long things take. And the third one is a much more generic, almost a framework for event simulation. So you could take one of these for your project too, and just remember the things that you need to kind of deal with here. Just to remind you is that your system is going to have some state. You're going to have to define what the state is. It's going to be like a mutable struct or like a struct containing a mutable array or something that's going to evolve over time. And then a series of events, and the events might be different to the ones we've seen. For instance, if there's multiple queues, you might have to tell the system somehow which queue is being added to or subtracted from in that event, right? So that might be some associated data in the event or something like that. And the third thing, like the previous simulators that you can change is you can have this callback, which is intended for performing measurements of the system, okay? So just to remind you, you got different tasks in Project 2. So for different tasks, hint for the last task, you might actually need to start changing things, like have a different kind of set of events and state, or different callbacks to perform different measurements. And that's just the way it'll be. But feel free to take this code, feel free to change this code. You can hook in with the hooks that are there. You can also obviously change that main event loop or something if it suits you in some way. It's really up to you to write the code to get the answers to the problems. Don't forget, I believe is there pracs this week? Yeah, there's pracs this week still. Some of you still have pracs. Yeah, we kind of ended, we got partway through this heap data structure. So this was a data structure where the, let's say the soonest event, the event with the time, which is the smallest time, will be at the top of this heap. And what we want to do is be able to add and take things out of this queue. So we can add in queue events that are going to happen, and we want to be able to get the soonest thing. So the heap is a data structure that lets us do that. So let's say you had a tree like this, just to remind everyone quickly, because we kind of only got 3/4 of the way through the explanation. If we have a tree like this, we always keep it balanced in a very special form so that if we add an element, it's like this tree, but with an extra one here, where my mouse is, if you can see that, okay? And if we remove an element, if we pop, well, obviously we're going to use that one, but what's going to be missing at the end of some rearrangement of all the nodes, what's going to be taken away from the system is this one down here, right? And there's always this sort of top down, left to right kind of fill in pattern, all right? It's always sort of dense, let's say, in this sort of pattern. If we think of left and right as 0 and 1, and we write that in binary, we can kind of think of these as indexes to an array, which is how you would do this more efficiently than what the demonstration is here. And we have these very basic balanced tree structure. So this is not the sorted heap. This is just a really basic one, which lets you put things in and take things out of the tree in the same order without any sorting. And we saw there was this push function, which sort of basically traverses down the nodes to get to the point where you're going to add where the hole is going to be filled, and a pop function, which goes down the same trajectory and finds the hole that's going to be the last element that's going to be popped off or removed from the tree. And then the last bit is all about enriching that. So here when we do the tree, when we push everything in, pop everything out, all that they just come out in reverse order. So what you put them in. But with the heap, what happens is when you pop them out, they actually come out in sorted order. So the smallest things first. And to do that, what we do is we don't only just put, let's say, put the element in that slot. If it's it might not end up resting there. We may actually swap it with its parent or its grandparent in order to have this property that that all the elements are smaller than their parent, are larger than their parents, because we're talking about a min heap. So if all the elements are larger than their parents, the one at the top will be the soonest time, all right? And so you kind of think of two steps to this pushing. The first is you put it in that spot, and the second is you do this operation called sift up. So because bubble it up until it gets to a point where it doesn't need to swap with its parent anymore. And that's sufficient to enforce this condition that every parent is larger or smaller than its child, depending if it's a min heap or a max heap. And then very, very similarly, if you're going to pop, you're going to pop the thing off the top, and then you're going to basically rearrange things so that there's now a hole at the top of this. We're going to push that hole down, like that hole. We need to kind of fill in that hole with the bigger or the next biggest or next smallest element, and continue doing that until that the element that should be missing to maintain this sort of dense balanced structure is missing. And that's the whole point of this sift down logic. And the logic of these is very simple. It's really like just swapping a parent with its child, right? Like that's all these kind of manipulations here are. And so we use it like that. And so what we can see is if we put everything in and we pop everything out, they come out in, well, this is a max heap, so they come out in reverse lexical order. All right, so the opposite order to dictionary. And that was that. So that's just sort of like a lightning recap of what we did yesterday. That's in a way the heap is sort of background material, and we're going to go through now some help for talking about like how you might go about building your software in Project 2, Project 3 to be a little bit more modular and manageable and reusable and things like that. So now that we just spent a lot of time talking about the heap, what we're going to do is we're going to imagine providing a heap data structure for other people to use. So like for example, I work in a software team, and some of us might write libraries and some of us might write application code which consumes those libraries, right? And you know, if you get two programmers in a room, you can obviously pair program on one keyboard, but it can be more efficient sometimes if you can have two different computers and you program two different things in parallel. Or if you had 100 programmers, you know, it's better if they're doing 50 things in parallel rather than one thing with 100 people around one keyboard, right? So you want to make sure when you're building a large amount of software, it's more and more important to make things modular so that you can do teamwork and you can parallelize your efforts and reuse other people's code in your code and things like that. So modulars. So obviously modular means just something's like a Lego brick that can just be sort of self-contained and live on its own. That's a module. So Julia has a bunch of modules in it. Some represent kind of like standard libraries and things. So when you open Julia, let's just go here. Let's open a Julia terminal. I prepared these earlier. So there's actually a few modules in here. There's a module called core, and inside core are things like core.compiler, I don't know, the return type or something. So like, for example, this is a function that's part of the compiler. And you can do things like, what does the sign function return if you pass it a float 64? And you know, that's where all the compiler specific stuff's done. So Julia will use functions like return type to compile your code and make it fast, right? And then there's another function called another module called base. It comes with Julia. So just to prove this, the type of base is module, right? So And base has all the things in it like sine and plus and all the kind of things. Sorry, you have to use weird syntax for that. It has all the things in it that you're going to use as a Julia user, right? So it's not, base isn't for the purpose of writing the compiler, that's sort of separate, but it's for everyone using Julia. And then there's a function, there's a module called main. So main isn't really built into Julia per se. The REPL spins up a module main when it turns on, and that's something the REPL does. When you execute a script from the command line, by default, it creates the main module, but it's in no means special or anything like that. It's just the first module it creates by default, right? And so in Julia, you can create modules, right? So you can use, like we have the struct keyword and we have keywords like that. There's another keyword called module, and it sort of looks like this. You could theoretically like indent everything in here, but typically a module might be a whole file. So that's like, you have to indent every line then. And so we just don't bother indenting everything. And so what lives inside the module are things like variables and functions. Now, you can access things inside the module using the dot syntax. So just note that, like, we normally use that dot syntax for something like, let's say, a complex number. I'm having trouble typing today. So that's actually a struct with fields like z.re and z.im. So we normally use that dot to represent, get the field of the struct, right? That's normally what that means. But it also works on a module, and you can kind of think of like a module like this as being sort of like a struct, but it's sort of dynamic in nature. At runtime in Julia, you can add new things to a module. So when you go to the REPL and I type like x equals, ooh, don't know what happened. Oh, well, that's actually kind of useful. Anyway, x equals 1 or something, right? Now I have inside here, I have main.x, right? And I had main.z defined before, right? So that's where it lives. And, you know, you can get any module and at runtime add new variables to it, or new functions or structs or different things inside them, right? Yeah. So, so for me, I always think of modules sort of like a dynamic struct in a way, or like something, you know, that the compiler manages over time. So well, I've mentioned this. By default, when you create a module, it imports the base library. There's a keyword called bare module, which is like, doesn't have any hidden imports or anything. You have to explicitly import even base, which may or may not be useful. But the other thing to note is that modules can be nested inside other modules. So you can make these namespaces for different bits of your code so that you can reuse variable names and things in different parts, or function names in different parts of your code base without clashing with each other. And, you know, so, with the naming, what's interesting is if I import a module, if there's a couple keywords, there's import and using, okay? If I import a module, that tells the package system to find that module on disk, right, or in the package system as a package. Packages are kind of related to a module in a way. And it brings that in, and it makes that basically like a variable in your current scope, in your current module. And then you can use that dot to get inside it, right? So if I had like a bare module and I get import base, I would have to go like base.sine to use the sine function. But if I go using base, when I use the using keyword, then I look at everything in that module which has been exported, and I bring them into my module as names as well. For example, we might put something like export variable or something, and then when you type using my module, you'll import not just my module, but you import variable as well. Now, using an import by default, go to this package manager. So the package manager is the thing where I'm going like using this thing, and I'm going like, you know, add plots or something. And if I did that, Why don't we use a small package? That's a small package. If we do that, it's going to go get this package. Actually, apparently it does have a bunch of dependencies. That's weird. Must have updated everything. It goes and gets that and downloads and put those files in special places for you, right? So that's a package. We won't deal too much with packages, or we might in a little bit. But that's the one I would go like using indexing. But if I put a little dot in front, that means I'm like, oh, actually, I'm referring to a module that's already loaded. I don't need to like look for files on my disk or something. This is a module that already exists, and I want to grab all its imports and start using those imports. Is import like all those exports? Sorry, start using all those exports. And you furthermore, like directories in DOS or Bash or whatever, you can use 2 dots to go like up a directory, so to speak. You know, go to the parents module. And like if you are creating modules, it's worthwhile naming them well, because you know your user is going to have to use this name. And so there's a rule that the module name can't clash with one of the exports, for example. And generally, like if a module is about a particular data type, it's common to pluralize it. So we're going to make a module for max heap, and we're going to call the module max heaps, right? That's just what we're going to do. Right? And so we want to create a module that people can import and use a heap. And to make it that a little bit more useful, because we don't know what people are going to do with it, we're going to add a type parameter t to the nodes and to the max heap, so that the value associated with the node depends on t, right? So that's the first thing we're going to do to make our code more reusable. And then what we're going to do is we're literally copying and pasting all the code that I zoomed through at the start of this lecture really quickly. And we're just copying and pasting all those functions in here. And because it's in this module, it's not like the main module is going to be polluted with names like sift up and sift down, which only really relate to this one data structure and nothing else, right? You never really want to use them on their own. They're just for internal usage of this module. But the thing you're going to use from this module is max heap, and that gets exported, right? So the things that are exported are somehow like the public parts of the module that you want everyone to play with, and the things which aren't exported and don't have any documentation, then you generally want them to sort of, they're hidden. If people start using them and you change your code, their code might break and that kind of thing. So yeah, so this is just, it's quite a lot of code here, but it's only copy and pasting the code we've already showed you. What we've got here, has anyone seen this before with the string in front of something? So this is called a doc string or documentation string. And so this is the one where you go like, you know, I can go sign, right? But I can go question mark sign. So like this is how you create this stuff, and this is in a markdown format, if anyone knows what markdown is. But that lets you have like these backput ticks sort of indicate code, for example. Yeah. And that's a module. So that's a way of taking some code that can be packaged up in a module and put in a box and put in a shelf, and then someone else can get it off the shelf and use it in their code, right? So generally in Julia, the files and the modules are completely almost unrelated to each other. Okay, so a module can contain multiple files. You know, a file can contain multiple modules. So long as the syntax within a file is complete. Like if there's a begin, and there has to be an end in the same file. But other than that, you'd usually like begin and end in a file and then include a bunch of files on the inside. And so the include keyword tells the compiler to go find that file and just basically take that text and paste it here, and then interpret the whole thing, right? But it's a little bit, it's sort of first parses it, so it has to be completely parsable without surrounding text, but then it just basically pastes that in. And that's sort of how that works. And so with module, using import, export, and include, you can generally build quite complex nested kind of software. Yes. Yeah, please. So yeah, that's a good question. So if we had multiple files, I'm going to need to find some code. Why don't I show you this? Because we're actually going to do a demo of a package. So the question is, how do we actually have multiple files per module, right? Yeah, so I'll show you this in a few minutes. Let me just talk about a package, and then we're going to create a package, and then we can add a few files to it and see how that all relates. So a package has, in Julia, the thing that you install generally, like plots or whatever, is designed as some code that can be shared. It can be sort of uploaded to a server and downloaded by other people, right? And so in some sense, it has to be modular. And in fact, every package contains a module. So in fact, if the package name is foo, the module has to be called foo, right? Also, there's a special place that expects to find a Julia file, and that Julia file should contain the module foo, or return the module foo. And that's sort of the expectation of the package system, right? So the packages have a name, and the name plays a special role. And then in the root directory, there's this thing called metpackage.toml. So toml's a file format, like JSON, CSV. It's a bit like the old INI format that they used to use on Windows, if people remember that. And I can show you one of those in a few minutes. And that has to contain like the name of the package and also some UUID. So what's the UUID? So that's a universally unique identifier. So it's basically it's like a hexadecimal string, 128 bytes of bits of randomness, essentially. And that way, if you create a module called foo and they create a module called foo and I import both of them, or whatever, they both live on the package server or something, people can distinguish them. Oh, I mean that one, not that one, right? And that way, because people tend to be working in different teams and have full visibility of the whole universe, it means that you don't have to worry about coming up with a universally unique name for your work. For example, if I'm doing private work and I create my own package for Alara, my startup, and then someone else creates a package of the same name in the open source world, maybe 6 months after I've started working on my original one, it won't suddenly break, right? It won't be like, oh no, you can't use this name anymore, it's taken in the public space. So that's what that's for. And then the package might contain a few extra optional things. It might contain a manifest file. Some people who use Python or JavaScript would know this as a lock file. So that doesn't specify not only, like this specifies which other packages you depend on, but this specifies the exact version of all the things you depend on, all the things they depend on. It defines an entire virtual environment that Julia will install, and you can kind of like run your code in a sandbox that is sort of deterministic. It's like, even if there's newer versions of certain things, they won't be installed. You'll get exactly the versions that you ran it at. So if you're doing a scientific thing, it's really important to create one of these files because they and share that file, because that defines the environment that your code runs in and might affect the behavior and the results you get. Right. So if you want to make everything reproducible, that's important. Typically in Julia, you put packages in a Git repository. It's sort of a loose relationship these days. And packages might have things like a unit test suite, which are really useful. Unfortunately, we're not going to do a lot of time on testing, but it's really cool to create those. Yeah, so I'm going to just give a quick demo of creating a package. So let's say I'm at the Julia REPL. I can press the semicolon key. That's this one, right, to get into shell mode, and I can do shell things in here. Where am I? I'm in here. Okay. So now I'm in here. So let's make a directory called demo or something. Demo. Right. All right, let's see what happens. Now I'm going to go into package mode and type gen. Is it gen? Generate. Generate. I don't know if we can do that. Oh, it's created another subdirectory. Okay, so it creates a directory, it puts files in it. And I'm gonna just open that in VS Code. And I'll just show you what it looks like. Okay, so in here, there's a project TOML, which contains a few things, like the name and the UID, and it contains this demo.jl. So it just has some default thing. So normally what I would do if I was writing a project, I'd have something like, it's a bit confusing. Sorry. Let's try and make that a bit bigger for everyone's probably this one. So I might create like an extra file here, file1.jl, right? File2.jl, right? And in this main one, I might do things like include file1.jl. Like that. All right, and so now I have a package with a file that this is the file Julia will run when you import it when you go import or using on it. And then this will immediately load these other files, which can have whatever I want in it. And then I can create directories here. I can create modules with submodules inside this package to organize all my code. Okay. So if you want to write something complex, you can do all that. And then in Julia, I can actually like add, I think I can add, yeah, this will work. So I think if it doesn't know it as a package, oh yeah, here we go. Sorry, you can tell it to use a directory, right? Yes, sorry, develop. I can just tell Julia to start tracking this package, and then I can go like using demo. And demo doesn't have much in it. I said before, it includes things like base, but it'll also include eval and include. So you actually get an evaluation context for each module. And so these are like those kind of built-in functions for evaluating code and stuff in that module that Julia uses, which is kind of interesting, but okay. Cool. So what time have we got? We got past. Now, I'm probably going to skip over this because I'd like to have enough time so we can start talking about data and unit 7. But before I do that, does anyone have any questions so far? What have we got up here? What's the difference between packages and modules? Do you feel that was answered with some? Like a module is sort of inside of a package, and a package is managed. It's a bunch of files managed by the package system. Thanks. Anyone have any questions or like concerns about project 2 or something they'd like to raise or anything like that? Yeah. For example, I'm using files that sort of use. Yep. Okay. So the question is, do I need to compile my module or something? So if you're using Julia, typically the base Julia thing expects the code to sort of stay static. It's for running complete programs, right? So there's a module called, a thing you can install called Revise. And what will that will do is when you have a module or a package installed, it will actually track files you change. And so you don't have to constantly reload them. Now, what the question really was is if you have like a module, not a package, but a module in a file, and you have other files importing it, Julia might complain that you're replacing that module. So basically, every time you go include, it's actually running the code in that file, and it's going to define a module in the scope of your thing, and it's going to have the same name as the last time you ran it. Okay, so it actually create a brand new module. Inside that module will be brand new types of brand new functions. They'll happen to all have the same name as everything before, but Julia will kind of treat it as separate code. So I would just sort of say that's actually not too dangerous. But like if you're moving this to like a production setting, you'd start to use the package manager and stuff to handle all that. You just be a little bit more careful about loading that once. One thing I've done before is you can ask Julia if something's assigned. So you go like, is assigned? Is this assigned? So I can go like, I can ask like, is this thing exists is defined maybe? There's some function like this. Where you, yeah. Whereas that would be false. So you can ask whether this thing exists and then conditionally load it and stuff. But if you do that and you change the code inside your module, you won't reload it. So you'll be stale, that'll go stale. So it's sort of hard to know what's the exact right thing to do there without going full on with the package system. I don't know if that's helpful, but yeah, just know it's not like a huge, it's not going to make your code incorrect. Yeah. Anyone? Yes, sorry. Yeah, difference between packages and modules. So module is like a data type built into Julia, and it can contain other stuff like a struct, right? Whereas a package is external to Julia. Julia has a package manager, which like takes files from the internet and installs them on your computer so that you can run that code. And that's the two levels. I think the expectation is that every package contains a module, but you know, you can't say that Julia code contains packages, right? Like it's sort of outside the Julia code world. It's more about the whole, you know, the system that the Julia environment will install those files for you. But in terms of code, packages in a sense don't exist. Only modules exist. Yeah. Is that helpful? Yeah. So there's the Julia programming language. So yeah, I would say the package almost exists outside the programming language of Julia, the code, like the code that you type, right? It has certain semantics. There's no built-in object, which is package, right? There's a built-in object, which is module, which can contain submodules and things like that. And then there's a package manager, which can install files on your computer. And when you type using this, it knows to include certain files and things like that. So it's sort of like an orchestration system for code. It's a way of plugging code in together is the package system. And the modules are more like just code itself, I suppose, maybe one way of putting it. Yeah. Yeah. Oh, the module is, yeah, parsed code or something. Cool. So yeah, I know a little bit about this stuff because I have done some open source packages and programming in Julia, and do a lot of sort of closed source packages these days as well. So yeah, if anyone's interested in this, you can ask me about it at any point. But if we can, oh, here we go. There's Emon. There doesn't seem to be a lot of difference between using an import. Should we use one over the other, or does it not matter much? So the only distinction between using an import Emon is that the using keyword will import everything that's exported and give them variable names inside your local module, whereas import will not. So you'd have to go, you know, if you import a package, you'd have to go like package.func, package.f, package.x, you know, this kind of thing. And that's the only distinction. So in terms of the capability of them, they're equivalent in sort of power. It's just how you feel like organizing your code. Some people would argue that using might be somewhat dangerous in that, you know, different packages might happen to change under you and they might export the same thing you're already using inside your package. And that might make your code a bit unstable or something. Julia will always warn you if that happens, but still it's better to avoid it happening. So with some other programming languages, you would always use import, for example, and use dots to get into things. That's how you might, that might be a standard thing to do in Python, for example, you know, or JavaScript. I'm just going to talk for a few minutes about Monte Carlo and statistics, and I'm just going to gloss over this and move on to data, okay? So we did allude to Monte Carlo a little bit earlier, So what we've done is a kind of straightforward, stochastic simulation, right? We've got probabilities and we can just predict the next thing in time going forward, right? So there's not a whole lot of statistical trickery going on in these simulations, but you can do some really interesting things with statistics and with computers and with randomness and Monte Carlo. So generally, the Monte Carlo method is often used for finding an estimate of something, right? That's one way of thinking of what you might want to do. And, you might want to use the same code and take estimates of many things, right? So like in project 2, you might want to find estimates for the average queue size of each queue, right? So you might be making more than one estimate. But let's say we're just talking about the expectation value of a scalar. What you could do is you could take some random samples and just take lots of random samples and just divide them by n, okay? But we don't always use this form of estimation. So sometimes you use something called importance sampling, which means you might fiddle with the probabilities. You might look more at, some versions of X might be more probable to draw than others, okay? So in this example, what we've done is we're just basically summing G over all possible X's with equal weight. So, one way of doing this is you could literally enumerate all possibilities and add them all up and divide them by n, right? That's one thing you could do. Now that's usually very slow because usually there's a high amount of possible configurations, or maybe an infinite number, right? So what you could do is you could just pick random ones and have some sampler G. But what we typically do is we want to choose the X's which are more probable more often and the ones that are less probable less often. And then what we actually end up estimating is G actually has less variance in it when we do that with importance sampling. And so if G has less variance, then we need N to be smaller to get a certain standard error, for example, or error bars, right? So we're interested in sort of estimating G to some error bars, and the question is, how many N's do I need to actually achieve that level of error? So you can actually do transformations on the system so that the variance gets reduced and you can get acceptable error in less time. So which might be taking, from the time of the universe, the age of the universe, like so many billions of years or whatever, and turning that into 10 seconds, right? So this can be a big difference. And so this is the whole idea of importance sampling and variance reduction, is that basically you change the distribution X that you draw from, and that rescales the relative weights of the G's, and you can do that in a way such that the G's become almost equal, then the variance of G is getting smaller. So I don't really want to talk about that too much, but that's something that we do. And we in a sense, we're already doing that in our simulation because we are sampling according to probabilities. We're not randomly sampling the space of all possible trajectories. We're really picking ones which are more relevant and more likely. Markov chain Monte Carlo. So we were talking about this whole ergodic theorem yesterday or last week, I can't remember. But the idea here is that if you have some system and you evolve it through time, it reaches some sort of stochastic equilibrium, right? Where the distribution that it has is something you're interested in. And so you can often frame problems, especially Hamiltonian problems, if you're a physicist, in a way such that the distribution you get from some dynamics is like some thermal equilibrium, or like it's something of interest, right? For example, in physics, you might think of maximizing the energy with respect to some mean, and maximizing the entropy with respect to some constraint on the mean energy, right? And this is thermal equilibrium. So that maximization problem can be solved. That's an optimization problem. It can actually be solved by transforming it in such a way that you're actually doing sort of dynamics, which reaches some distribution, which happens to equal the thermal distribution, right? And what will happen is you just sort of like, you pick some random state. And again, if you imagine those bouncing balls in the ideal gas simulation, you pick some initial state and you let the system evolve for a while. It'll kind of end up looking kind of random, so long as it's sort of like chaotic and exotic and stuff. This is the sort of Markov chain approach, is that after enough time, the system, like that might be a deterministic case, the bouncing balls, right? But you might do this with some randomness in the evolution. Like, for example, if you're interested in filling the plane with disks that might be bouncing off each other, you can actually kind of like propose randomly moving the disks rather than following a motion. And then you can still sample the statistical ensemble of all possible configurations. But you're not using a deterministic simulation, you're using a random Markov chain approach from going from one configuration to another. And it still satisfies the same distribution after a long enough amount of time. And so that's what the Markov chain Monte Carlo is all about, is you're using, and I'm going to skip over this because it's not actually going to be assessed or something like that. But you use some statistics to actually figure out what the sort of distribution is. And I don't know if there's a nice, yeah, we don't have a nice stochastic trajectory here, unfortunately, but yeah. Yeah, and here is a point of interest that was probably a little bit more relevant last year, but here we're starting to talk about the models that people use for like modeling COVID rates of spreading and things, where you might have SEIR model, epidemic model. So SE and INR are the different populations that might exist. So people who are susceptible, they don't have any immunity to a virus. There's people who are exposed. So that means, let's say you've been in contact with someone with a virus, but you're not yet sick. So it's in that containment period. And then infected, so that'd be the red line. So you have symptoms and you're contagious to other people. And then there's removed. So this is a little bit of a nasty reality of the fact that once people are either recovered or deceased, it's kind of equivalent from the point of view of the epidemiology. So they just get put into the removed bucket. So hopefully they survived. But if not, then you don't have, you've lost 85% of society. So that's not very good. And this is why we see these waves of like the Delta virus and the Omicron wave and things. It's like you get a new thing and then you get another. This dynamics plays out every time you get a mutation or something like that, or it becomes winter and the rate of transmission increases or something like that. Okay. That was fun. I hope you guys enjoyed Unit 6 and enjoy the let me click. There we go. Enjoy Project 2. It is actually a bit of fun, so try and get through it. I just want to spend the last 6 or 7 minutes of this lecture introducing Unit 7 and talking about data. Okay, so data is really important. So if we're doing mathematics, applied mathematics, we're trying to solve real world problems, we're going to need a lot of real world data. Okay, so it really pays, like if you don't have like a computer science background, it really pays to learn a little bit of how people store data on computers, right? So you probably all use something like Excel before, but that's not how your bank manages your bank balance, right? It's going to use a different system. It's probably going to use a database, which is a dedicated program that runs on a dedicated server to keep your data safe. And it's going to have lots of interesting features that make that data safe. So it's the database itself is a system which lets people store and access data in a way such that the data won't get lost. And if you try and like change the data in the system, it doesn't get confused. For example, databases often have this concept of a transaction. So if I give you money and something goes wrong, some computer program crashes, you don't end up in the state where like my bank account was deducted and no one received the money and the money's just deleted, or vice versa. You don't get money, their balance doesn't increase without my balance decreasing, right? So the transaction means you have to increase this and decrease that and then commit the transaction as a whole thing. And so databases provide features for that kind of thing. Okay, and so the most common kind of database that you'll see used, especially in the business world, is a relational database. So it pays a lot to understand relational databases and the language that people use to interact them, which is SQL. So some of you will kind of know all this, and it's boring, and for some of you this will be all new. So I'll have to go through it. Okay. So SQL's a kind of an old language. It looks a bit different to the languages you see today. It's sort of like when they invented it, they're like, oh, we want to invent a language that, you know, that isn't for like electrical engineers and physicists and like people that have spent 20 years learning how to program the ENIAC computer or something. You know, these are for everyday business analysts that haven't used computers much. And so they made the language look a little bit like English. You know, so it'll say things like select X from table and things like that. And it's almost like writing miniature sentences when you get it to do things. Okay. So we're not going to cover SQL in detail here, but I just really want to emphasize, like, as someone who's been in academia and now the industry, it's sort of like a very practical skill that's worth paying attention to for your careers ahead, you know. But what's really underlying SQL is this idea of relational algebra. So I'll spend a few minutes talking about that, and then we'll come back and we'll continue this lecture on Monday. So a relation is actually a mathematical concept. So you all know what a function is. If you have f of x, y equals f of x, right? You can imagine having a tuple, which is like a list of x's and the associated f of x's, right? And so a relation is a list of all those tuples. So that might be a finite set, like you might have the not operator on Booleans. So x might be true and y might be false, and x might be false and y might be true. And that's the entire relation. The relation is the set of tuples. And so that set is of size 2 and has those 2 entries in it. There are 2 entries excluded. You can't have true, true and false, false, right? But you could have the relation with all 4 possibilities, or you could have the relation that's empty with none of the possibilities. So a function is a special type of relation which has a kind of a single entry for each input x, let's say, or it could be have multiple inputs, like functions can have multiple inputs, right? But a relation is a generalization of this, where like if you take the square root function, you know, the square root of 1 is 1, but the square root of 1 is also -1, right? So the square root, you might be more correct to talk about the square root relation than the square root function. Or the inverse of sine, that's also like a relation, right? So there might actually be infinitely many solutions to the arcsine of 0. Well, arcsine is defined as a function, but like the inverse sine of 0. So that's what a relation is. It's a set of tuples. They usually have names, which are like the names of tables. Okay. And in computer systems, you normally think of finite, you know, discrete relations that you can store on a disk rather than like abstract, infinite mathematical ones. But the whole idea of relational algebra is that you basically store things as tables on disk, and the relations, like in functions, you can compose functions. You can go like f of g of x, for example, and you can compose functions together. Well, you can compose relations together with this operation called join, and you can bring all the data together. And so that's just a little bit of an introduction. We're actually out of time today, but I'll just run through what we're going to do next week. We'll talk a little bit about how to use relational algebra and how we're going to use that kind of data in Julia using this data frames package. So we're going to end up seeing tabular data in Julia, and we're going to learn how to load it, how to query it and manipulate it, filter it and group it and aggregate it and all these things. Okay, and so these are going to be like really fundamental steps to you working with data as a mathematician. Okay. So that's going to be the whole purpose of Unit 7, which will lead into Unit 8, which is taking data we've loaded and doing inference on it with machine learning, which is lots of fun. So, okay. Nice to see you all. I'll see you all on Monday. I think there is a student consultation tomorrow as usual. So I'll see you there too if you need it. Yep, thanks. Thank you.